All right, so now we're going to talk about a special class of modules called projective modules. Well, there's two. There's projective modules and there's injective modules. And in a general abelian category, there's going to be projective objects and injective objects. But again, we're just thinking about modules here. So let's look at this diagram. P to Q, there's some map F. These are all modules. And then this bottom map here is surjective map, and we'll call it phi. Now, we say P is projective. So P is projective if whenever F is any map, whenever F is any map at all, any map, and phi is surjective, then we can lift F to a map from P to Q to a map P to R, and we'll call this thing F tilde. Then we can find a lifting of F. Can find a lift F tilde of F. So we can lift the map from a map P to Q to a map P to R, and that happens when phi is surjective. And there's a dual notion called injective where the diagram looks like this. I'll just draw it, but we won't talk about it any more than that. This bottom map here is injective, and it's a lift that looks like this, right? And you can put your F's and things in. We won't talk about that. So this one's called injective, the top one's called projective. You can think of this as capturing a property that you want, that free modules have. So, well, here's a proposition. Every free module is projective. So proposition. Every free module is projective. And this is kind of straightforward enough to show because, well, let's think about it. We can map P into Q, but, well, since P is in particular free, well, let's call it F. We'll make a new diagram, actually. So since F is free, we have a basis. So let's just prove this. I was going to talk through it, but let's prove this. So we have let A be a basis for F. All right, then let's take an A and A and look at F of A. Well, since R is surjective, then there must exist an S in R such that phi of S is equal to F of A. Now we can define a map. We'll call it F tilde, and it'll go from A to R, and it's defined by sending an A to the element S. And you can check that this is the right map that makes the diagram commute. And this is defined on A, but we extend it by the universal property of free module to all of F. I mean, you can do that obviously, right? You define a map on a basis. Provided you have a basis, it's easy to extend it to the whole module. So done. There's our proof. But that requires F to be free because we need to be able to extend from a basis. So here's another proposition that will come up. If we have a short exact sequence, and the last module here is projective, so this is a short exact sequence, and P is projective, then the sequence splits. I'm not going to prove that. It's a diagram chase. And lastly, one last proposition is that a projective module, a module P is projective if and only if it is a sum end of a free module. So P projective if and only if P is a sum end of a free module, And we prove that by using the proposition before. So consider this short exact sequence where F is free. We know since every module is a quotient of a free module that there's going to exist an F and surjective map such that we have this short exact sequence, and we know it's going to be exact if we just include the kernel. But P is at the end, so it splits, and we get, and there we go. P is some end of a free module. That's the end of that proof. There's not much more to it than that. Right. So yeah, as I said, there's a notion of injective module, and all these kind of results are dual. Right. You have some of the arrows flipped and things, but it's pretty much the same thing. And okay, so now let's think about something called a resolution. So we're going to use our projective objects, projective modules, resolutions. So we should think of a resolution as a more general form of a presentation. And we remember from Murray's talk, we talked all about presentations and free groups, so this should be kind of familiar. We think of these resolutions as generalized presentations. So let A be an R module, B an R module. So a free resolution is an exact sequence. Free is an exact sequence. Well, it's a free resolution of A, I suppose. It's an exact sequence. We'll call it F, and it's this long sequence of free modules, and then it ends with A. So yeah, as I said, we think of this as a generalized presentation. I'll just say where each Fi is free, where each is free. So, for example, in the category of groups, it's pretty easy to make a finite length free resolution of each group. For example, as we talked about with the free group and the presentations and stuff, let's consider a group G, and then here's a free resolution of it. And we know that every group is a quotient of a free group, so we can write down this as a free resolution, and it's finite length. And the generators of the kernel of pi are the relations in G, right? Because we remember from how to construct how a free group is constructed as a quotient of how a group is constructed as a quotient of some free group. So we know that this exists, and it's finite length, and that's really good. So this is the same thing as a presentation. Now, when we go to the category of R modules, we can't do this. Why can't we do this? Because the kernel, well, because a submodule of a free module is not necessarily free in the category of R modules. It's different. In the category of groups, every subgroup of a free group is free. So when we're talking about groups, our kernel here is free. But that's not the case more often than not at all for free modules. So we're gonna have to think of a different way to make this free resolution, and it's no harder. So proposition: every module has a free resolution. Every module has a free resolution. Okay, so we'll start with the same exact sequence that has the kernel of some quotient map, and we'll call our module A again. We'll call this one pi and this one I. Now, well, okay, kernel of pi, well, that is a module in its own right. So what if we constructed a little short exact sequence for our kernel of pi on the end? Because that's a module, and this can be pi1, and this can be I1. And we can keep going, right? We can now make a little short exact sequence for pi1. And what we do, I'll just write proof. And what we do is we can kind of weave these short exact sequences together. So we'll start with A, and we have F going to A, and then I'm going to draw it bent, but you'll see why. So, and then we have another free module, F1, and then we have, what's this? This is kernel of pi1. So I should put these maps in pi1, that's a 1. This one's pi, and then we do it again. These need to have zeros to indicate that it's exact. Then we do it again, F2. I'll draw it a bit higher so everything lines up. I want it to be neat. F2, kernel pi2, ta-ta-ta, right? And you continue this. Now then, how do we construct our free resolution? Well, if you then, so we want a map between all these f's, and all we do is we take this map to be the composite of the quotient maps, these pi maps, pi2, and then that should be inclusion 2. This should be pi 2. This should be I2. This should be I1. So we take these horizontal maps here to just be the composition. So the composite of these two maps is this map, and I'll call it D2, and I'll call this one D1, right? So it's just the composite, and you can check that since these short exact sequences are exact, that this new exact sequence that we construct going along, we do it inductively, we can check that that's exact, and indeed it is, and it's a free resolution. It may be infinite. It will terminate if one of the kernels ends up being free. But other than that, it's going to be infinite, and it's a free resolution. So we're done. I mean, I guess we have to check exactness, but that's a diagram chase. I'll leave that to you. Right, and again, we can think of this as a generalized presentation. The kernel of this map is going to be the relators that make up F, and then the kernel of the next one is going to be the relators that make up the kernel of the previous one, and so forth. So now we're going to define a similar thing called a projective resolution. And it's going to be a free resolution. Well, it's not. It's going to be a resolution, but instead of free modules, they're going to be projective modules. P0, A0. And we'll usually call these maps D as well. D2, D1. And this one always gets called epsilon for some reason. This is called a projective resolution. And then we make something called the deleted projective resolution, where it's the same, except at the end, we drop the A. Because we don't need the A. Why don't we need the A? Well, A is equal to the co-kernel of D1. So we don't actually lose any information by doing this. Why is this true? Well, co-kernel of D1 is P0 mod im D1, which is equal to P0 mod the kernel. The image of D1 is equal to the kernel of epsilon. And we use the first isomorphism theorem to see that this bottom map here is an isomorphism, because the last map has to be surjective. So indeed, A is equal to co-kernel of D1, and we haven't lost any information at all. And yeah, I'll remark that there's a dual notion where instead of projective objects, we use injective objects. It's all the same, right? Except it goes the opposite way. I'll let you figure that out. So now we have resolutions. We have functors, we have categories. We're going to put all these things together. And what we're going to try to do here is fix the fact that tensor is only exact on one side. We're going to do it using all this stuff. So I'm going to call this bit derived functors. Derived functors. Right. So, first of all, let's take our category of R modules, or just some general abelian category. And we're going to, for each object in that category, we're going to pick a projective resolution of it. We know that we can do this in our modules, that every module has a projective resolution. Oh, I should have said that. Every module has a projective resolution. Why? Because free modules are projective. So in particular, this resolution here we made is a projective resolution for every module. So there's a condition on an abelian category called, you say an abelian category has enough projectives, and that just means you can make a choice of projective resolution for every object. So first of all, we're going to, for each object, we're going to make its deleted resolution, right? P1, P0, 0. For every single object. Now, we're going to have some covariant additive functor that we want, and it's going to be called T. And it's going to go from one abelian category A to another abelian category C. And additive just means that it does this. And since, okay, I should have said this earlier, I suppose, but since our categories here are abelian categories, the Hom sets are actually abelian groups. So this addition is addition on the Hom sets. And the property that T is additive is just this property here. Right. So we have a covariant additive functor. We have a projective resolution. Now, let's just apply T to every projective resolution to make a new thing. So I'll remark that the projective resolution is an element of comp A. So now we're going to make a new sequence thingy, and it's going to have T applied to it. We apply. Oh, I wrote P0 twice. This should be P1, sorry. And we'll call these maps, this can be D1, so this will be T of D1. And then we'll have, we'll have T of D2 here, etc., right? So we apply T to everything, and we get this new thing. It is a complex, so the reason why it's a complex is because of this additivity condition. I'll show you. So if you go T, D, N, Dn plus 1, right? Oh, maybe I've got those numbers backwards. No, that's right. This is equal because T is a functor to Dn, T, Dn plus 1. Right, but on this, so this is the composite of the horizontal maps, but this is T of 0 because the initial thing was a chain complex. But T of 0 is equal to 0 precisely because of this additivity condition. If you write T of 0 as T of 0 plus 0, and then you split it, and then you'll get T of 0 plus T of 0 is equal to T of 0, but, indeed that means that T of 0 has to be 0. So the additivity condition is what guarantees that this object is now in comp C. So what we've done, we've taken an object of A, we made its projective resolution in comp A, then we've taken it to comp C. So that's where we're at now. We're now in comp C. Now, there is no reason to think that this sequence will still be exact. Our projective resolution is exact, but as we've seen, functors break exactness and stuff a lot of the time. So we want to check how much it fails to be exact. And the recipe for checking how much something fails to be exact is by taking homology. So let's take the homology of TPA. And we're going to rename this, and we're going to call it LNT of A. Homology is a functor, and T is a functor, so their composite is also going to be a functor. And homology now takes us from comp C to C. So now our whole process takes us from A to C as a functor. And this functor we're going to call LNT, as I said here. Now, we know how homology acts on morphisms as well. So let's say we have an F from A to A prime in A. This is going to give us a chain map, F tilde from P of A to P of A prime. And then we apply T to F to get a map TF, I suppose you're right, TF tilde maybe, from TPA to TPA prime, so TPA to TPA prime. And then we apply homology, and homology we want it to go a map from, so LNT of F, we want it to go from LNT of A to LNT of A prime. A lot of maps going on, but again, this just works the same way a normal homology functor map would work. So FZ, right. I always get confused here. That's just the way the homology map acts. It might be mildly confusing. Just think about what homology does. So this LNT thing is indeed a functor because it's a composite of functors. It's a composite of additive functors, so indeed LNT is even additive. We call this family LNT the left-derived functors of T. So left-derived functors of T. And you do the same thing with injective resolutions instead of projective resolutions, and you get something called the right-derived functors. So here's a definition. So if we set T is equal to the tensor product, then LNT, we define it to be called, just a new name, it's called Tor N R, and you put a blank here, and then B. And this is called the Tor functor, and Tor functor is going to be how we fix up our tensor. And, well, T takes a right R module and gives you a left R module. Well, let's just pretend R is commutative, so then T takes a right R module, or it takes an R module and gives you an R module. So if R is commutative, this is a functor from R mod to R mod, like this. And as a remark, you can do the same thing with right-derived functors and hom, and you get R nt. So if t is equal to hom, then you get, this is called xnr, like this, right? So that's if t is equal to the hom functor that we talked about at the start. Now my mouse has died. This is a bit annoying because I'm trying to scroll down. Okay, yeah, so you want t equal to hom blank and then b like this. Right, so some properties of Tor. I'll just kind of say what each is. I'm not going to prove any. Well, actually, I'll prove one. So properties. It's symmetric. Well, it's sort of symmetric. Tor n r a b is equal to Tor n, and then you pick the opposite ring. But if R is commutative, we don't have to worry about that, and we'll just pretend it's commutative. Well, I should probably say this is isomorphic. Whoa, I just erased the t. I should probably say this is isomorphic. Tor respects direct sums, so if you have Tor, then some direct sum of modules. This is equal to the direct sum of Tors. Third property, it's not just direct sums, it's something called filtrant colimits. You just replace the direct sum symbol with the colimit symbol. But yeah, no, it doesn't really matter all that much, I suppose, because we won't be using that. If we had more time, we'd get to talk about all that stuff. So, okay, my scrolling's not working. This is excellent. Here we go. Well, here's where Tor gets its name from. It's related to torsion. So Tor1, and we're Toring abelian groups, so it's Tor over Z. Where, so Tor of Z mod PZ with A is equal to AP, and AP is the subgroup of A generated by elements that have order of P, or order P. So I'll say AP equals the A in A, such that PA equals 0. So these are abelian groups. And the proof of this, so proof. Let's take a projective resolution of Z mod PZ. And I can write one explicitly. And this is mod P, and this is times P. Now, here's a projective resolution. We take the deleted resolution, so we chop off PZ, and then we apply Tor. Well, we apply tensor, and then we take homology. So let's first apply tensor. These are tensors over Z. I should probably include those. And remember, we chopped off the end already. Now, this map here is going to be times P tensor the identity on A. Now we want, so Tor1 is equal to the first homology of this thing. So H1 of this complex, well, it's going to be equal, so this is the first map, so the image of the zero map, no, sorry, it's going to be equal to, right, kernel of this map, so ker times P tensor 1A, mod the image of the previous map, the image of the previous map 0. So it's just the kernel of times P tensor 1A. So what's the kernel of this map? Well, there's a few ways to think about this, as we did before, and we saw that this map will kill the elements that have P torsion in A, but a best way to think about it is that the map Z tensor A to A that sends an NA, that sends an N tensor A to NA, this map is an isomorphism. So we can think of the map from Z tensor A to C tensor A as the map from A to A that multiplies by P. So they're kind of the same map, right, if you think about it that way, because these things are isomorphic. So our map times P tensor 1A is the same as the map from A to A that takes an A and sends it to PA. And of course, the kernel of this map is going to be our subgroup of elements of order P. So it's AP. Right. If you want to recover all of the torsion, that's the next property. Tor 1, no, I should put Z. Z. And then we want to take Q mod Z, A, and this is equal to the torsion subgroup of A, which is the subgroup generated by all elements of finite order. And the proof is much the same. Let's take a projective resolution of Q mod Z. So this is the inclusion, this is mod Z, right? Take, chop off the end, tensor with A. Now this is the inclusion tensor, the identity on A. But, so let's think about how the kernel of this map works. It's going to be the kernel again by the same argument. So the kernel of this map, it sends an n tensor A to n tensor A, because it's just including Z. We just include the integers into our rationals. But we can write n tensor A as np over p tensor A, because Q is divisible. Then we can move the p from the top over, so this is equal to n over p tensor PA, which is equal to 0, right? Because A has some order P, and we can do this for any P. So if it's got, I don't know, P plus 1 torsion, where you just replace P with P plus 1. So you can see the kernel of this map is all the torsion of P. So we've proved this. And indeed, if you erase the A from here, then this thing here, this is a functor, and indeed it's naturally isomorphic to the torsion functor. And you do the same thing. You can do the same thing with modules. If you take tor R and you take the fraction field, frac R, mod R, and blank, and this is naturally isomorphic to the torsion functor, which we'll call T. Right. Now, here's the kind of last property, the last thing that we'll get into here today. And let me find the exact sequence. Here we go. So, if we have a short exact sequence, a short exact sequence, and it's just going to be ABC again, I think. Oh, I call it A prime. So A prime, A prime prime. Then, these are R modules, right? Then there is a long exact sequence, and it looks like this. It goes tor R N A B. It's infinitely big. Well, it might terminate, who knows. Tor N A prime B. Tor N A prime prime B. Then it'll be tor N minus 1. And back to A. Dot dot dot, right? And it keeps going. More arrows. Then it goes tor 1. A prime prime B until we get here. And then it goes to tensor. Then it goes A tensor B. A prime tensor B. A prime prime tensor B. And this is the exact sequence. So if you'll recall, tensor was only exact on the right. So when we tensored with a short exact sequence, we got this part here. And kind of the rest of this sequence, this whole tor part, it might be finite. If it is finite, it's kind of even more useful. But we can look at it, and it kind of tells us to what extent that this leftmost map here fails to be injective. And it kind of fixes the fact that tensor wasn't exact. It tells us how much it's not exact by. There are some conditions when you tensor with some rings and it is exact. For example, things with no torsion, right? The kernel is still going to be trivial. So we can think about kind of tor modules as somehow fixing the exactness of tensor for us. I mean, it's a little bit more involved than that. But I mean, I don't think we have time to go into all the, there's a million different properties of tor that we could go through, and they're quite fun. But I think the way we should think about it for now is it's kind of telling us maybe how to fix the exactness of tensor, and it's telling us that by giving us some ideas about the torsion. And you should think of these tor modules as somehow encoding the relative torsion between A and B. I'll write that relative torsion. Relative torsion is an important concept. I'd like to end on an application called universal coefficient theorem. So earlier when we talked about homology of a topological space, so let me just write a new heading, universal coefficient theorem. So earlier when we talked about the homology of a topological space, we defined Hn of a topological space X to be the homology of the chain complex, right? So now we're going to define the homology of a topological space X with coefficients in an abelian group A to be the homology of the triangulation complex, but everywhere we're going to tensor with A. And remember, these things are all free abelian groups, so we're going to tensor over Z. Well, A is not free abelian group, just any abelian group, but we're tensoring over Z. And similarly, there's a notion of cohomology, which I'll just write it down for you. Oh, it's that, the n goes up. We define the cohomology of X with coefficients in A equal to this. Then you take hom. And then like this. Right. So this is cohomology over here. This is homology. Now, first of all, why does the abelian group you pick matter? So for example, the kind of information that you get from this invariant changes. So I computed an example of a Klein bottle. And you can find that I computed cohomology. H2 of K with coefficients in Z is equal to 0, but H2 of K with coefficients in Z mod 2Z is equal to Z mod 2Z. So you can see that what coefficient ring module, whatever you pick, abelian group that you end up picking, it does matter. It'll change your invariant a little bit, and maybe it can be used in a more powerful way if you can, change coefficient ring or whatever. So now, let's say you don't have the complex Sx. You only have the homology, but you want to find the homology of the complex with different coefficients. But since we don't have the complex, we can't just tensor in and then check the kernels and images again. We're going to have to, find another way to do it. So first of all, you might think that if you have Hnx and you want Hnxa, that you could do this. But this doesn't work. This doesn't work at all. It's wrong, because think about how torsion breaks things, and the torsion in Hnx and the torsion in Hnx with coefficients in A, they're going to be all kind of wacky different stuff going on. So this doesn't work. So I'll give you a theorem. I can say the theorem in full generality. I won't. I'll just write down the result. So theorem. There is a short exact sequence that goes like this. Oh God, Hn Sx, and then we're going to tensor A, and then I want Hn Sx, and then we're tensoring A on the inside, and then the last one is tor 1r Hn minus 1, like this. And so this shows exact sequence, and it splits. This short exact sequence splits. If it splits, we get an isomorphism. Remember from earlier, Hn Sx tensor A, and we're going to direct sum with tor. It's a lot of writing. I won't bracket it. And then A, and this is isomorphic to Hn, or Hnxa, which is what that middle thing is. And so yeah, that's one way which tor can be useful. I just kind of wanted to highlight one use of tor, and it kind of it does allow us to be able to change your coefficient ring of homology just by, using tor or whatever. And you can see that our formula up here, this actually does work if there's no relative torsion between Hn minus 1 and A, or if either of them are torsion free. Indeed, this formula also does work. So yeah, I mean, this is one application of it. I mean, it's kind of, I'm trying to sell this to people to do analysis, why you might want it. And I guess here's my selling point, is that it can tell you a bit more information. It can give you a better topological invariant in this particular case when we're doing singular homology. I'll end on one remark, and it is that sheaf cohomology is the right-derived functors of the global sections functor. So if I did another one of these talks, I would like to talk about that, and it gives a lot of good motivating examples for all this derived functor business that it seems like abstract nonsense and just a bit of mental masturbation, but truly there are a lot of good examples, and this stuff was developed, not to be abstract nonsense, but to solve problems of things like, stalks of holomorphic functions and that sort of stuff. And there's also a lot of good examples in de Rham cohomology, where you have the de Rham complex, and you can look at the space of differential forms on manifolds and stuff like that. So that would make another good talk. But I think I'm going to wrap it there for today. If you made it this far, I appreciate it. I appreciate the listening. Thanks.